Okay, 6-8, number 1. This is the classic falling stick problem. All right, so we start with a stick completely vertically, and we're going to let it fall. And we're going to let it accelerate, and then they ask us a bunch of questions. What's the velocity? What's the angular speed when it gets horizontal? What's the acceleration, angular acceleration when it gets horizontal? What are the x and y components of the linear acceleration of the center of mass when it's horizontal? And then what are the hinge forces? Hinge forces are super weird. They're super counterintuitive. We'll talk about it when we get to that. So we got our falling stick, we got our center of mass, and to find the velocity when it gets horizontal, we're going to use an energy approach, right? Anytime you're asked for a final velocity or something about speed, and distances involved, you want to try to use an energy approach. Another reason you know why you want to use an energy approach is because here in this position the torque is 0. There's 0 torque because the weight force is vertical and the radius or lever arm is also vertical, so they are not perpendicular at all. So we've got no perpendicularness. There is 0 torque here, where here when it's horizontal the weight force is down and completely perpendicular then to your lever arm here. So we have a varying torque, which means we're having a varying angular acceleration, and anytime your acceleration is changing, you want to try energy. Otherwise, you'll have to use calculus in your dynamics equations, and we want to avoid that, even though we could. So, what energy do we start with? Clearly, it has some potential energy, but how do I find it? Well, we're going to use the center of mass as the mgh height. So you can kind of even see as the stick falls that the acceleration is varied. It starts out moving really slow, and then the acceleration picks up. So we got our h is going to be half of the length of the stick. All right, things given, I think, are the mass of the stick and the length of the stick. So everything's got to be in terms of those things. So there you go. And then what the final energy here is, then we're going to say 0 potential, since this is the lowest point the center of mass reaches. In the case that we're studying, if it were to fall below this point, then we need to add in more potential energy. But we're just going from here to here. So our height is L over 2. L over 2. I think that's what that says. And then our final energy is all kinetic, so 1/2 I omega squared, where this is a stick rotating around its endpoint. So we can look up on our cheat sheet, or maybe by now you know it is 1/3 ml squared, as opposed to 1/12 ml squared if it were rotating around its center. You can also find that using the parallaxis theorem. But rotating around the endpoint of a stick is pretty popular. That would be one of the formulas I kind of have in the back of the head. We got our 1/3 ml squared, our 1/12 mr squared, and then you should probably know a disk as well as 1/2 mr squared, because almost everything's always a disk. And then you simply plug things in and you solve for the final speed, angular speed, 3g over L rooted. All right, that's part A. Not too complicated there. Just use an energy approach. All right, second part, finding the angular acceleration. So questions about acceleration you can't use energy for. You're going to want to think torques or forces. Luckily, they aren't asking us to find like the acceleration at a different point. Then we'd have to involve an angle or whatnot. Like I said, the torque here is variable, so it goes from 0 to maximum. So we're at the maximum torque, which means we're at our maximum angular acceleration when it's horizontal. And we know it's maximum because then the weight force is perpendicular to our lever arm, which is again L over 2, because it's acting at half the length of the stick from the pivot point. So Newton's second law for torques, sum of torques then is your mg force acting at a radius or a lever arm of L over 2. It's a stick around its endpoint, so 1/3 ml squared, and then angular acceleration is what we're solving for. One quick step of algebra, we get 3g over 2L. So there you go, so that's part. Third part starts getting a wee tricky. They're asking for the x and y acceleration. Okay, so how do we know it's accelerating in the y direction? Well, it's falling, right? That's pretty straightforward, right? It's falling down. The center of mass is moving down. It's speeding up as it moves down. There's still a component of mg that's down, so we know the center of mass in the y direction is down, right? So we've got that. Boom. How are we going to find that? Well, if we know the angular acceleration of the whole stick, then we can find the linear acceleration or the tangential acceleration of every point along the stick using our relationship that tangential acceleration is alpha r, where r is the point that you care about. So knowing that relationship, since we found the angular acceleration in the second part, we can use the angular acceleration and the distance to center of mass to figure out the tangential acceleration. And at the horizontal position, the angular acceleration is, or the y acceleration is tangential to the circular arc it's tracing out. So we plug in our angular acceleration and we get 3/4 g. So it's not really falling at 9.8, it's falling at 3/4 of 9.8. Vertically. Okay, here's the weird part, right? The center of mass is actually tracing out an arc, right? As this thing falls, the center of mass is moving in a circle. That means there has to be some sort of centripetal force and centripetal acceleration acting. So how are we going to find that? Well, that's going to be the acceleration in the x direction. It's going to act at the center of mass and it's going to point towards that hinge point or that pivot point or the axle, whatever they call it. So our acceleration in the x is actually our centripetal acceleration, which we can find if we knew the velocity at that point and at the radius at that point. Good thing is, we know all those things from part A. We can find the tangential velocity using the angular velocity that we found in the first part. So knowing that tangential velocity is omega r, just like we know tangential acceleration is alpha r, we can sub that into our centripetal acceleration, which simplifies then to omega squared times r. So what's omega squared? Omega squared from part A is 3g over L. So that comes from the first part. And then what r do we use? We use L over 2 because they're asking for the acceleration at the center of mass. So that all simplifies then to 3 over 2g, which is interesting because that's more than 9.8. It's more than the acceleration due to gravity. So we actually have an acceleration in the horizontal direction towards the pivot point that's greater than 9.8 because this thing is changing its direction, right? Centripetal acceleration is the rate of change of direction. Here is when it's changing its direction the fastest because this is where it is starting to slow down and stop speeding up, I believe. No, maybe. Okay, so we'll talk about that in a later part, right? Actually, if we look at these accelerations, if here is 3/4 g in the vertical direction, there's some other points here that maybe at a greater radius are actually also accelerating at a higher than 9.8. So it's a little weird because you would think a falling stick, right? If gravity is the thing making it fall, then how can it accelerate at a higher rate than 9.8 in either direction, whether it's the horizontal centripetal direction or the normal vertical direction? Turns out you can because there's other forces acting on it other than gravity, which is what part D asks us about. It asks us what are the forces from the hinge point. So what are the forces on the hinge? If it's accelerating down and to the left, which by the way, when you do the problem, make sure you put the negative sign in your answers for your accelerations because they are arbitrarily calling left and down negative. So we have a negative horizontal acceleration and a negative vertical acceleration. That means we should be able to identify forces that are causing those accelerations. Now, if we look in the x direction, if it's accelerating in the x direction, there has to be a force there. Well, there's nothing else touching the stick except for that hinge. Without the hinge, there can be no left and right force. So as this thing's swinging around, you kind of have that centrifugal or that outward feeling, right? I mean, like standard thing, you drive a car, you turn left, you feel like you're being thrown towards the outside of the circle. You can imagine that same feeling as the stick is falling. It thinks it's getting pulled out, right? Because it's inertia. So inertia wants that center of mass to keep traveling in a straight line or in this straight line, but it can't. So there's that hinge force that's fixing this part of the stick, keeping it moving in a circle as opposed to with a constant velocity. So I know I have to have a horizontal part from the hinge that is also inward towards that circle or to the left in the negative direction that's causing that horizontal acceleration. So net force then in the x direction is mass times acceleration in the x direction. The only force that, or the only thing we can even identify touching the stick that could cause that is the hinge itself or the axle itself, and so then the hinge force is just mass times the acceleration, the x, which we have from the previous part. For the force in the y direction, we got to add those up. If you can kind of imagine, right, if the stick were falling vertically, I can justify an upward force from my hinge to get this rotation to happen. If there is no upward force here from the hinge, then the stick is gonna fall straight down. But if there's something in a way, like an axle or a hinge, that center of mass, using its inertia, wants to keep going down, but if there's something in the way pushing up, that'll cause it then to rotate around this hinge point. So I know I have a hinge force up, and I have a weight force down. I'm gonna add up my forces in my y direction, so I have that positive force from the hinge, and I got my negative weight force down. That's equal to mass times acceleration in the y. Boom. Simple algebra. Plug in your answer from part C, and you got it. Hinge forces are not intuitive. They kind of do require a little bit of playing with a stick and thinking about how am I going to get that center of mass to actually swing in a circle, and how am I actually pulling the whole time. Right, you got to put yourself in the frame of view of a hinge, which is a weird thing to do. Hopefully that one helps.